Welcome to the deep dive. Today our mission is, well, ambitious. We're cracking open one of the deepest ideas in physics. If you've always thought of Fermi-Lara, Newton's second law, as sort of the absolute ground floor, prepare for a shift. We're moving beyond just forces and acceleration to explore something, frankly, more elegant. The principle of least action.
That's right. It's a really different perspective. Newton's laws, they tell you what happens moment by moment, right? Force now means acceleration now. But the principle of least action, sometimes called Hamilton's principle, it asks a different question. It asks why a particle takes the specific path it does between a start point and an end point. It shifts the whole problem from solving differential equations step by step to finding a path that minimizes something.
A global view instead of a local one. Okay, so the core idea revolves around this thing called action, symbol S. Can you break that down? What exactly is this action quantity?
Sure. Action S is defined as an integral over time. Specifically, you take the kinetic energy, Ke, subtract the potential energy, Pe, and you integrate that difference over the entire time the particle travels, from the start time, T81, to the end time, T2 tolls. That difference, Ke minus Pe, it's so important it gets its own name, the Lagrangian. We usually write it as math call.
Math call, okay. So C dollars is the integral of math call over time. C dollar in val call dTd. And the big idea, the really profound bit, is that the actual path nature chooses is the one where this S value is an extremum, usually a minimum.
Exactly, that's the principle. Nature is, in a sense, finding the path that makes this integrated quantity, the action, stationary, typically minimized.
Okay, let's dig into that. Why? Why should minimizing Ke minus Pe over time give you the real path? It sounds almost intentional, like the particle knows where it's going.
Well, it's not about knowing, it's more about efficiency. Think about a particle moving, let's say, in gravity. If it deviates from the true path, things get less optimal. If it goes too fast unnecessarily, its kinetic energy shoots up. That makes the Ke part of the integral bigger, so S increases. But if it goes too slow or takes a longer meandering path, the time it takes increases. And since you're integrating over time, that also inflates S.
I see. So it's like a trade-off. Go too fast, S goes up. Take too long, S goes up. The actual path is the one that balances these two, like finding the sweet spot.
Precisely. Imagine throwing a ball upwards. It follows that familiar parabola. If it tried a different path, maybe spending way too long hovering at the top where Pe is high but Ke is low, the overall time integral S would actually be larger. The real path is the one that averages out that difference, Ke minus Pe, over the whole trip in just the right way to make the total S as small as possible.
That helps frame it. It's like trying to drive somewhere. You don't want to floor it the whole way, waste gas, high Ke equivalent, but you also don't want to take some ridiculously long scenic route that takes forever. The best path is usually the most direct, a compromise.
That's a good analogy. The straight line, if there's no potential field, is indeed the path of least action. It's the compromise.
Okay, so conceptually it makes some sense. But how do you actually prove this? How do you get from minimizing S back to good old-fashioned
Right. This needs a mathematical tool that might be new to some listeners. It's called the calculus of variations. It's different from regular calculus, where you find the minimum point of a function, like the bottom of a valley fact.
But slow down. How is it different? Regular calculus finds the lowest point. What is this? Calculus of variations find.
It finds the lowest path, or rather the optimal path or function itself. We're minimizing a functional that's a function of a function, or a function of an entire curve. Think of it like this. Take 2 points on a hilly landscape. Ordinary calculus finds the point with the lowest altitude between them. Calculus of variations finds the shortest path you could walk between those 2 points while staying on the surface of the hills.
Okay, finding the best curve, not the best point. Got it. So how do we apply that variational calculus here?
Well, the basic idea is you take the true path, let's call it 6t, then you imagine disturbing it slightly, making a varied path. We write this varied path as 6t plus eta tt is some small deviation, like a wiggle. And here's a key constraint. This wiggle, dr, has to be 0 at the start and end times. The path has to start at A and end at B, no matter the wiggle in between.
Right. You fix the endpoints. Then you compare the action for the true path, h in dollars, with the action for the slightly wiggled path, 6 day.
Exactly. You calculate the difference delta S S best. The condition for SST being the true path, the path of least action, is that for any tiny wiggle theta, the first order change in action, delta theta, must be 0. The action is stationary.
Stationary, meaning if you wiggle it just a tiny bit, the action value doesn't really change to a first approximation.
Correct. Now, this involves some mathematical steps, Taylor expansions, integration by parts. It gets a bit involved on paper.
Yeah, I bet. And honestly, it sounds like a lot of complex machinery just to what shows something we already knew, does it actually lead anywhere useful?
Oh, absolutely. This is where the magic happens. When you go through those steps and you set that first variation, delta says it to zero, what pops out? You get an equation. $1 fracts to second.
Hang on, your knowledge tracks it. That's mass times acceleration.
Yeah.
And v phi, the negative derivative of potential energy, that's force.
Precisely. It's $5. For any system where the force comes from a potential energy, what we call conservative forces, minimizing the action integral is mathematically equivalent to Newton's second law.
Wow. Okay, that is surprising. You start with this very abstract, global idea about minimizing an energy integral over a whole path. And out comes the fundamental, local, instantaneous law of motion, Feynman goal. That really suggests this least action principle is, well, more fundamental.
Many physicists believe so. It feels like a deemer explanation why Feynman holds.
Okay, but we derive this for a simple particle in one dimension, right? What about the real world? 3 dimensions, multiple particles, relativity, electromagnetism. Does the principle still hold up?
It does, and that's the real power of this Lagrangian approach. The principle of least action remains the same. Find the path that makes stationary. What changes is the Lagrangian. Instead of just spiral pi, you use a more general Lagrangian that encodes all the physics of the system.
So math call becomes more complicated depending on the problem.
Much more, potentially. For instance, take a single particle moving relativistically near the speed of light through an electromagnetic field. The Lagrangian needed to describe that motion looks like, well, it's math K, math Euro C2, square 1 V2 C2, math BFE A. Okay, that's quite a bit more involved than CTP. I see the relativistic energy term and then terms with potentials in FBFA, BFP.
Exactly. The first term handles the relativistic kinetic energy. The second part handles the interaction with the electric scalar potential phi and the magnetic vector potential math BFE. But the amazing thing is, this single function math cal, when you plug it into the action integral CFE dt Diller and find the path that minimizes S, it gives you the correct relativistic equations of motion, including the Lorentz force law for electromagnetism. Everything is unified under this one principle.
That's incredibly powerful. One principle, just needing the right math call. Okay, this is clearly fundamental for classical physics, relativity, E&M. But the outline mentioned quantum mechanics. How on earth does a principle about finding the single best path connect to the fuzzy, probabilistic world of quantum?
Now we get to maybe the most profound connection of all. This insight is largely thanks to Feynman himself and his path integral formulation of quantum mechanics. In quantum mechanics, a particle going from point A to point B doesn't take one path. It sort of takes all possible paths simultaneously.
All paths, like literally every conceivable wiggle and detour between A and B. How does that even work?
It sounds crazy, I know. But the idea is that for each possible path, there's a probability amplitude, a complex number. And the total probability amplitude to get from A to B is the sum of the amplitudes for all those infinite possible paths.
An infinite sum. How does that lead back to the single definite path we see for, say, a baseball?
Through interference. And this is where action comes back in, crucially. The phase angle of the complex probability amplitude for any single path is directly proportional to the classical action samara calculated for that specific path. The phase is basically $0 divided by Planck's constant, phase per bar.
Okay, 0 bar. Now, Planck's constant gar is tiny, incredibly tiny. And for everyday objects, the action dollars is, well, it's usually a pretty big number, relatively speaking.
Exactly. So the ratio bar is enormous for almost any macroscopic path. This means the phase changes incredibly rapidly as you move from one path to a slightly different neighboring path. If the phases are changing wildly, when you sum up all the amplitudes for these paths, they point in all different directions in the complex plane and cancel each other out. It's massive destructive interference.
So most paths just vanish. They interfere themselves out of existence.
Pretty much. Except for paths very, very close to the path where the action dollar is stationary, usually the minimum. Near that minimum action path, Sampledar doesn't change much when you wiggle the path slightly. That was condition delta S equals R. So the phase bar is also nearly constant for paths in that vicinity. These nearby paths all have similar phases. Their amplitudes add up constructively.
So the classical path, the Feynman the path of least action, it emerges because it's the only one where the quantum probabilities don't all cancel out. It's the result of constructive interference.
That's the core idea of the path integral view. The principle of least action isn't just a classical rule, it's the very condition that allows a classical path to emerge from the quantum fizziness. It selects the coherent trajectory.
Mind blown. Okay, that links classical and quantum beautifully. Let's shift gears slightly. We've talked about minimizing action over time. Can we use similar minimum principles for static situations like finding electric fields?
Yes, absolutely. The universe seems to like minimum principles all over the place. For static electric fields, we're not minimizing action over time, but we are minimizing a type of energy stored in the field, in space. The correct configuration of the electric potential, in Veal, in a region is the one that minimizes a specific energy-related integral, let's call it $.
Okay, so for electrostatics, the field settles into the configuration with the lowest possible stored energy. Makes intuitive sense, like things settling into stable states.
Exactly. This quantity $, isn't just the field energy, it also includes a term for the interaction with any charges present. The integral looks like $1 dV over long. Here, dollars is the charge density, and that first term within Vol.2 is related to the energy stored in the electric field itself.
And minimizing that integral, what does that give us? Does it simplify finding the potential Landauer?
It turns out that finding the function finger that minimizes the Staller integral is mathematically identical to solving Poisson's equation. Nabla it's a set of Röstelon, which is the fundamental equation of electrostatics. So nature arranging the potential finger to minimize $1 is equivalent to satisfying the standard field equation. It's another powerful way to think about and solve field problems.
Can we use this minimization idea practically? Say if solving Poisson's equation directly is really hard for a complicated geometry.
Yes, definitely. It's fantastic for approximations. Let's take a classic example. A cylindrical capacitor. Two concentric metal cylinders, radii and volars. We want to find the capacitance $2. The exact answer involves a logarithm, propto 1ln(b). But maybe we don't know that, or it's difficult to derive.
Okay, so how would we use the minimum principle instead?
You could start with a guess for the potential cilia between the cylinders. Maybe just a simple linear guess. Assume Sealer changes linearly with distance from the axis. That's probably not right, but it's simple. You plug this linear guess into the formula for $2, or technically, into the formula for capacitance derived from energy. You calculate the capacitance based on this guess, and you actually get a surprisingly decent approximation, especially if the gap between the cylinders is small. The formula comes out like Ceilprox propto frac b plus EBO.
Not bad for just guessing a straight line. But what if we need better accuracy?
Then you improve your guess. Maybe try a quadratic function for $2, but include an adjustable parameter, let's call it alpha. Now you calculate the capacitance dilly using this more flexible quadratic guess. The result will depend on alpha. Then you use calculus to find the value of alpha that minimizes the calculated capacitance dilly.
So you vary your guess using the parameter alpha until you find the guess that gives the lowest possible capacitance value.
Exactly. And when you do that, when you find the alpha that minimizes $dollars for the quadratic guess, the resulting capacitance value becomes extremely close to the true logarithmic answer. The minimum principle guides your approximation toward the correct answer. It's a very powerful technique for complex problems where exact solutions are tough.
Fascinating. So even for practical calculations, thinking in terms of minimization can be really useful.
Absolutely. So, to wrap up, the principle of least action isn't just some clever mathematical trick. It seems to be a truly deep statement about how physics works. It underlies classical mechanics, it extends naturally to relativity and electromagnetism via the Lagrangian, and incredibly, it provides the bridge to understanding how classical behavior emerges from quantum mechanics.
And we saw this idea of nature finding minimums isn't limited to action. It applies to electrostatic energy, and as the source mentions, there are similar principles in thermodynamics, like minimum entropy production, or even finding current distribution in circuits.
Which leaves us with a rather deep question to ponder, something for you, the listener, to think about. Why is our universe described so effectively by these global optimization principles? Why does nature seem to choose paths or configurations that make some overall quantity an extremum, instead of just operating based on local, instantaneous forces?
What does it say about the fundamental structure of physical law that these elegant overarching principles work so well?
It certainly suggests that looking at the whole picture, the entire path or configuration, reveals a different, perhaps deeper layer of reality than just looking at the moment-to-moment interactions.
A very elegant and challenging thought indeed. Thank you for joining us on this deep dive.